Great, thank you very much. Hi, everyone. My name is Kim Trenbath, and I am from the National Renewable Energy Laboratory in Golden, Colorado. Today, I'm leading the presentation on the Jump into STEM webinar on occupant-centric building controls. My presenter today is Dr. Michael Kane from Northeastern University. Before Michael Kane starts his presentation, I'm going to give you a little bit of background on Jump into STEM. Jump into STEM is sponsored by the U.S. Department of Energy's Energy Efficiency and Renewable Energies Building Technologies Office, with support from the National Renewable Energy Laboratory and Oak Ridge National Laboratory, or ORNL. Our vision with Jump into STEM is to inspire the next generation of building scientists by focusing on supporting creative ideation and diversity in the building science field. The Jump into STEM program provides a gateway or on-ramp for undergraduate and graduate students to experience the research and career possibilities of studying building science. Our intent is to attract students from diverse majors and diverse backgrounds. The Jump into STEM student competition is managed by Mary Hubbard from the U.S. Department of Energy, myself, Kim Trenbath, and Jahi Simbai from the National Renewable Energy Laboratory, or NREL, and Melissa Lapsa and Dr. Yanjin Bae from Oak Ridge National Lab. Jump into STEM is open to any student enrolled in a U.S. college or university. We have a professor team representing schools such as Georgia Tech, Hampton University, the University of Tennessee, the Colorado School of Mines, Southern University, Clark Atlanta University, the University of Alabama, North Carolina A&T State University, and Tennessee State University. These professors will promote the Jump into STEM at their school, and many offer it in their classrooms this fall for a semester grade. We also have an advisory panel representing Oak Ridge National Lab, the National Renewable Energy Laboratory, the National Science Foundation, and Oak Ridge Associated Universities, and they provide us guidance on outreach into the program as a whole. With Jump into STEM, our goals emphasize cultivating diversity of thought by underscoring the importance of interdisciplinary teams inclusive of women and minorities. Jump into STEM works with university and college professors from a variety of disciplines to support creative building science challenges that can be integrated with coursework curricula. Jump into STEM's network includes leveraging public-private partnerships with industry partners and STEM organizations to support the annual student challenges and events. With this slide, you can see a quick snapshot on how the Jump into STEM student competition works. Eligible students can compete for up to 4 paid internships at either Oak Ridge or NREL. Students can go to jump.ideascale.com and navigate to the homepage by clicking on Return to the Jump into STEM website. On this Jump into STEM website, they can view eligibility requirements and the full schedule. From the Jump into STEM website, you can click on How it works at the top of the page to view a step-by-step process on eligibility, building a team, ideation, and idea submission requirements. Also on the top navigation bar is the schedule for the Jump into STEM 2019 to 2020 competitions. Eligible students can participate in any of the 3 concurrent online challenges running now through November 15th. These challenges are supported by an online webinar series, including this one, and these are designed to provide insights on industry practices, market issues, and other supporting resources to help students build and generate their idea solutions. After the 3 challenges close on November 15th, the Jump into STEM team will run a judging process to select finalists to compete on January 31st, 2020 in a final event competition that will be hosted by either NREL or Oak Ridge. During this final event competition, judges will award the 2020 Jump into STEM internship winners. Please go to jump.ideascale.com for details on how it works, eligibility requirements, and schedule updates. Next, I'm going to go through the 3 challenges that are open now and will close on November 15th. The first challenge is focused on smart sensors and controls for residential buildings. Participating competitors interested in this challenge should develop a unique application that uses sensor data in residential buildings for the purpose of reducing energy, maintaining or improving occupant comfort, and to provide better responsiveness to the electric grid. Strong ideas will present a proposed approach, identify the sensor data, and how the data will be used. The idea should also discuss the anticipated impact and a tech-to-market plan for the application. The second Jump into STEM challenge topic is to design a healthier and energy-efficient air distribution system for the small commercial building setting using your local climate zone. Strong ideas will identify a novel system for the selected climate zone and will present implementation of the solution in a hypothetical or an existing building. Solutions should articulate the expected impact from the design system and also include a tech-to-market plan. The third challenge topic is focused on pushing the envelope with innovative wall retrofit designs. Students are challenged to design a residential wall retrofit product or system that can address replacement or supplement current leaky and unhealthy walls. Strong ideas will identify how the wall retrofit will work and will be inclusive of details on how to address the issues of moisture and air tightness. Additionally, the ideal solution should address one or more of the following issues: low indoor air quality, high energy costs, or high retrofit costs. Like the other Jump into STEM challenges, this idea solution should include a tech-to-market plan. And the last thing that I want to go over before we jump into our technical presentation is the results from last year's Jump into STEM competition. At the final event that was actually held in April at NREL last year, our finalists were able to pitch their ideas in person and network with other students, professors, industry stakeholders, and lab staff. Here are some pictures from that final event. We had 3 internship winners from last year's Jump into STEM competition. Our interns, we had 2 interns at NREL and 1 intern at Oak Ridge National Lab. At NREL, Jump into STEM intern Cade Lawson worked on Comstock, one of the building energy modeling tools for the entire building commercial stock of buildings in the United States. Our Jump into STEM intern Sarah Tinsley worked at Oak Ridge on Energy Plus and Open Studio modeling. This is for commercial building energy modeling. And Carl Woodard worked at NREL on developing thermal energy storage through the use of phase change materials. At this time, I would like to introduce our technical presentation and our technical presenter, Dr. Michael Kane from Northeastern University. His topic is going to be on occupant-centric building controls. Dr. Michael Kane received his BS degree in architectural engineering and his MS degree in Civil Engineering from Drexel University. He has an MS in Electrical Engineering and a PhD in Civil Engineering from the University of Michigan in Ann Arbor. Dr. Kane is an assistant professor of Civil and Environmental Engineering at Northeastern University. Prior to this, he was a fellow at the United States Department of Energy Advanced Research Project Agency for Energy, or ARPA-E, in Washington, D.C. Currently directs the Automation for the Built and Living Environment Lab at Northeastern, and his research interests are in the areas of bilinear and hybrid control and human-in-the-loop control of infrastructure systems. And at this time, I'm going to turn it over to Dr. Kane for his presentation.
Thanks for that introduction. Can you hear me?
Yes.
Great. Let me switch it over to my screen. Looks like a fun jump in the STEM program. Looking forward to kind of seeing what the submissions are on idea scale. But before that, let's do a little bit of introduction about why we're doing this and methods that you might want to approach, especially if you're doing the sensing and controls. So you can see the first slide of the PowerPoint?
Yes, thanks.
Great. All right. So once again, my name is Assistant Professor Michael Kane at Northeastern University up in Boston. And we already got a nice introduction on my background. Yeah, so did my Bachelor's of Science and first Master's at Drexel University in Philadelphia, and then jumped into doing a little bit of electrical engineering, got electrical engineering master's and a PhD in civil engineering at Michigan, and really just showing how interdisciplinary this field is of building energy efficiency. Worked on applying that for 2 years as a fellow at ARPA-E. So if there's any graduate students in the audience, especially maybe first year PhD students, check out ARPA-E. It's an excellent organization that funds really cutting edge research across the energy landscape, from building energy to the grid, to batteries and chemistry and physics. And after leaving that fellowship, I'm now an assistant professor at Northeastern University. So let's talk a little bit about some of the research that I've been doing here with my students. But before we do, I want to open open with a thought experiment. So I hope everyone in the audience is following along and engaged. So I want you to think about it's the middle of winter, so it's cold outside, and you're trying to save energy like the energy efficient person you are. So you set back your thermostat to 65 degrees while you're away at work. You return home and you want it to get warmer. You want to feel comfortable again. What do you set your thermostat to? And I want you to think about that answer and compare that against what your thermostat might be set to on a normal winter day. We'll come back to this in a little bit. As we kind of introduce why we're working on this problem. And I think that the biggest thing that if you follow what ARPA-E does and you follow what DARPA and any kind of leading research institution does, before they start any research project, and I hope that you do the same, before you start any research project, ask yourself, if it works, will it matter? Am I doing this just to kind of like intrigue my own curiosity and learn more? Or am I actually trying to solve a problem that will really help the general population? And so we've been looking at building energy. It seems like this group, these seminars, is all looking at building energy. So I'm sure these statistics are no surprise to you. About a third of all U.S. energy consumption is consumed by buildings. And a large percentage of that is consumed by the heating, ventilation, and air conditioning, the HVAC system in buildings. And if we look at how those HVAC systems work, many of them have some sort of automation. There's some sort of sensors that are being perceived by some computer. That computer is computing on those answers and then ultimately deciding what to set the fan speed to, when to turn the heating or cooling systems on, things like that. But if we just think about buildings as the envelope, as the HVAC system, as the controls, if we just focus on that technical aspect, we actually do a really not too great job of determining how well our buildings are going to perform. Why is that? It's because a large percentage of this variation. So this is saying if we were to try to estimate how much energy a building consumed based off of just what type of dwelling it is, that's not going to tell us a whole lot. And even if we have two identical homes that are right next to us, they're not going to consume the same amount of energy. Why is that? So we can explain some of it about the building physics, but it's really about occupant behavior. Different occupants will operate buildings in different ways. So my lab and my PhD students here are really interested in working on trying to understand this problem of how do different people operate buildings? How can we help those people operate those buildings better with automation? Not replacing them, that decision making with automation, but really having them work together. And in order to do that, we're taking a data-driven approach using some big data techniques. And one thing that we're using is this Ecobee data set. So you might be familiar with the Ecobee thermostats. They're a competitor to Nest thermostats, if you've heard of them. It's essentially a smart Wi-Fi connected thermostat. And this data set actually is originally only had about 27,000 homes in it, but it's now up to about 80,000 homes where we have indoor temperature, outdoor temperature, why people change set points, occupancy information about every 5 minutes from these homes. So it's a really powerful data set to tell us about energy flows throughout a home, and the occupancy really tells us information about at least when people are doing things and where they are when they're doing them. We've used this to not only analyze this occupant-centric problem, but some other problems that affect kind of the individuals in a house of are they heating systems undersized or oversized? Are they undersized in heating or cooling? So what we've done here is we've looked through the data set and seen is the heating system or the cooling system on for at least 6 hours, and the HVAC system was never able to get to the set point. So in the winter, that means you're running your heater at full power and you're still not able to get to that 71 degrees that you're trying to keep your inside at or whatever the individuals had them at. And so kind of unsurprisingly, we see a lot of undersized systems in the northern continental US and a lot of undersized cooling systems in the Southwest. Well, this is a separate project, but I just kind of wanted to show you some other things that you can do with this data. But we talked about automation a little bit. And so what sort of things are those automation systems doing? And do those automation systems always have the same intentions as the person? And that's not always going to be the case because sometimes the person really just wants to be comfortable, but the automation system might be trying to do other things that the person really doesn't want to think about or isn't thinking about. And one of those, which is a really exciting new area, are grid interactive efficient buildings. So this is where the building is trying to interact with the electric grid in some way, whether that's to reduce load, to shed load, just reduce it over short periods, to shift load. So you might pre-cool a building in the early afternoon, and then that way you don't have to turn your air conditioners on when everyone else is already turning their air conditioners on. You might be able to save money on your electric bill. And then you might even be able to modulate and have your electric demand follow electric supply from things like rooftop solar or wind. The problem with automation is it often gets what the person wants wrong. And we see this in demand response programs here. We're seeing up to 30% of things that the automation system is trying to do being overridden or opted out by individuals. And if 30% of the times that a control system tries to do something, it's being overridden, it's not going to be a very effective automation system. So we should really try to reduce the overrides and opt-outs that we're seeing between occupants of a building and the systems itself. So let's look at building automation. So Building automation has been around for a while, a really long time, really. So I think about way back to the thermostat. This is a relatively new digital thermostat, but there's probably been a thermostat, and thermostats have been around for quite a while, at least 50 years, pretty much ubiquitous, and probably much longer than that. And pretty much what a thermostat does is that it replaces that person there feeding the fire in the basement. We no longer have to literally put fuel into our systems in order to have it um, to maintain the temperature that we want. The next kind of generation of controls were occupancy-based controls. So if you can see this little animation here, you might be familiar with this in your university or an office you've worked in, where occupancy-based controls try to turn off the lights when no one's there. But unfortunately, those don't always see you in your room. So maybe you have to wave your hands in order to get that motion sensor to detect you. We can do occupancy or like demand controlled ventilation. So by measuring how many occupants are in a room, we can decide how much fresh air to bring in a room, which saves us a little bit more. And the future is looking a lot more personalized. So can we have individuals kind of tell whether or not they're warm, whether or not they're cool? And there's companies that are already starting to work in this space. So what is comfort? We think about just like I like to first just start out thinking about how can we analyze comfort of a person? What is a person? What are people mostly made of? People are mostly made of water, and we can say that the average person, give or take, just to make the math easy, let's say the average person is a 150-pound bag of water. The average person eats about 2,000 calories a day. 2,000 calories, that's a unit of energy. If we take that unit of energy and divide it by 24 hours in a day, we get a unit of power. So that's like this person is converting food into movement and essentially heat eventually. How much is that? So if we take that 2,000 calories, divide it by 24 hours, it's essentially 100 watts. And we want to keep that 100-watt, 150-pound bag of water, we want to keep that at about 98.6 degrees. So we might put a little bit of insulation on it. We might put a sweater on. We might put different clothing on or take top layers of clothing off in order to maintain our temperature at that 98.6. So this just kind of gives a very, very simple model of what human comfort is. Let's dig in a little bit more about how this human comfort, how this person that wants to, all the primary thing they want to do is maintain their temperature. There's might be a whole bunch of other things that they want to do in addition to that. Um, so let's look at how this person is affected by the building and affects the building. So here we have a building where there's some sort of building automation and HVAC system, which is affecting the building physics, the internal temperatures. Those internal temperatures change the occupant behavior. A person might be too warm or too cold, and then go back and change that thermostat. So let's look at how we can model this system. Some of you in the audience might be familiar with Energy Plus. It's a software package developed by the U.S. Department of Energy along with Open Studio. So this is essentially tools for modeling building energy use. There's some easier tools like eQuest or some way more powerful tools like Trinsys or some other kind of tools that you might find throughout industry. Human physiology, we're pretty good at detecting this. This is essentially the model that we just talked about. This is that 150-pound bag of water with a 100-watt light bulb inside. And we can essentially map metabolic rate, your clothing, the air temperature, how much air is moving over you, the radiant temperature, the relative humidity. We can map those to whether or not someone feels neutral, hot, slightly cool. This is pretty standard practice in industry. The challenge is, what do we do when the person feels hot, feels cold, or only feels slightly cool? There's some pretty complex cognition that's going on when people are thinking about this. They might be thinking about, can they even affect it? Have you ever been in a room where you are cold, but you don't even bother getting up to change the thermostat, either because your parents are going to yell at you if you do, or your past experience has told you that that thermostat is essentially broken. It doesn't actually do anything. So we have to find some way to model this cognition process. There's a couple different theories that we're exploring, whether it's social cognitive theory or theory of planned behavior. And these ultimately end up with the person deciding to take some sort of action. But even saying, I'm going to take an action has some openness to it. What sort of actions can a person take? So let's come back to that thought experiment. I don't know. Is it possible to open the floor up to responses to this thought experiment? Is or is it should I just to keep on going with some hypotheticals here?
I think we can open the floor.
Is there a hand raising feature in this app?
There's a chat.
Yeah, I guess if you have your chat feature, anyone want to type in some answers about um, what you would do when you get home from work and it's 65 degrees and you want to feel warm? 75 degrees? Okay. Any other answers in there? We got 25 people on the line here. Let's come on. Let's get a little bit of audience participation. Okay, you usually set your thermostat to 70. Okay. 72 makes you feel comfortable. So Eric here would set it to 70. Maybe they're trying to save energy. So we have some motivations here. Um, Maybe some people are trying to set it up a little bit. We have one friend here from Canada using Celsius here. So where we can see that some people are trying to change their temperature in order to save energy, or even maybe save even more energy by putting on a light sweater. Um, and so we have some people that are saying that set it right to the temperature that they're comfortable with, and we have some people that are saying let's set it to a temperature that's a little bit higher than we're comfortable with. So those are different things. If we wanted to model the behavior of different people, we'd have to model both the physiology, the cognition, and what sort of decisions and actions they're taking. And so there's two major kind of theories about how people take actions. And another way to say this is that there's different mental models that people have about why they make the decisions that they do. People try to optimize their decisions, but given the limited information that they have. So the two theories are, quoting a research paper all the way back from 1985, one kind of theory says you just turn the thermostat up, and once she gets there to the desired temperature, you kick off automatically, and it'll kick on and off to keep it at that temperature. So that's the feedback theory. Valve theory says, or a person described it as essentially saying the thermostat is like a gas pedal. If you want it to get hotter faster, then you have to accelerate more. You have to press down on that gas pedal and really push it. Um, so uh, some of the responses, we got responses in both of these buckets here, but there's an issue with that valve theory model. That idea, I'm going to set this thermostat higher than I actually want it to be because I think it'll get there faster. The issue with that mental model is that's not actually how thermostats work. Thermostats are not valves. The way thermostat works is it works more like that feedback theory. If the temperature is below the set point, then the heating will kick on at full blast. There's no kind of in between in almost all modern thermostats. And then same thing for cooling. If you want it to get cold, set it to what you want, and it'll get there as fast as possible, and it will stay there. So this idea that different mental models affect not only how people interact with the system, but also affect the system performance. That the people might not be interacting with the system in an optimal way. So I hope that some of you who have valve theory might reconsider how you adjust your thermostat this winter. So let's look if we can see some of these behaviors in this ecobee data set. So what we've done is I saw that there was one person that responded. How was it that they responded? I like it at 22 degrees Celsius, but my wife wishes it to be 24 degrees Celsius. So there's issues where there's not only maybe mental models or things that you can affect yourself, but there's social factors as well. So in order to really process the data and to not get caught up in social factors, we wanted to really focus on individuals. We looked at the data set where people self-declared they're living in the home by themselves. So out of the 27,000 homes, there were 1,400 that were single occupancy. So significant cutback, but still, we have 1,000 people, and we have up to years worth of data from these 1,000 people. So let's look at maybe when people are overriding the automated settings of these thermostats. We see a lot of overrides in kind of mid-morning. So maybe people are waking up before their thermostat decides to get warm, or are deciding to sleep in past it and then or adjust it. Or maybe they're staying home that day and they don't want it to get set back to a lower temperature. Or we can see the difference between weekdays and weekends. And then we really see a lot of overrides in the evening. I like to joke about that last one is a lot of people will have their thermostat automatically set back to save energy at 9 or 10 o'clock. But if they got caught binging Netflix at 9:30, they don't want the house to get super cold during the winter while they're watching TV. So they override it and then end up keeping that override over the entire night. So we can see couple of these, I guess I had them called out, sorry. But yeah, so we see weekend periods between home and away, a lot more overrides during the weekend, because the kind of the varying of your occupancy, were you at soccer practice or did you stay home that day, or were you going in and out a lot is going to affect what you set your thermostat to. So what sort of things are these people overriding? Why are they changing the thermostat? What happened before the person changed the thermostat that made them decide to override it? And we can see here that half of the time that people changed the thermostat, they were changing a setting that they themselves had previously set. So this tells us that people are maybe not quite sure. Maybe they are setting it too high, overshooting a little bit, and then coming back. Other things that they might be overriding, or they might be overriding the default home setting. So maybe they're at home, they left away and they're setting it back to save energy, or it went to the sleep energy saving mode, but they were really awake, so they want to make sure that they stay comfortable. One thing that we can do is we can look at this data and see maybe about a third of the population uses this feedback theory, and maybe about two-thirds of and maybe about a third to half of the population uses the valve theory. And this is what we're seeing in these results, but we've also seen this in previous papers, some published in the 80s, some published in the 90s, that it's about a third of the population believes in this incorrect mental model of valve theory. So it's nice to be able to confirm this, at least kind of qualitatively, with some of the data. So if we wanted to design a better control system, might want to know, if we go back and look at these cases, how can we affect as the automation system? So the automation system can't really affect things that the person is doing that they themselves had previously done wrong. But they can affect everything on the right side of this pie chart, where things that the automation system was doing. So the automatic home settings, the automatic sleep settings, the automatic demand response settings. How can we design these better? And so what we've done is we've looked at the data and seen how long it takes for someone to notice a certain temperature change. So in this case here, it takes 10% or 11% of the population takes about 10 minutes to notice a 2-degree set point change during cooling season. We look at 30% of the population, it takes them within 20 minutes to change the temperature. And we can keep on populating this out to 100% of the population will notice the temperature change within 2 hours. So what we can do is we can actually make an entire plot of this data, and then we can even fit a line to kind of that average case. And we can say that on average, a person will notice a 2-degree temperature difference in about half an hour, while they'll notice a 10-degree temperature difference in about 15 minutes. So if we want to try to modulate the load, we should maybe we could modulate large temperature differences over short periods, but if we want really long periods of modulation, we can only use small temperature changes. We can do this for heating season as well. So that really wraps up kind of some of the approaches or one of the approaches that we've taken to learning from big data to really understand thermal comfort behavior as this process of physiology, cognition, and decision making. And then ultimately, we would like to integrate this into some crazy complex system that hopefully ends up not being that complex and really is interpretable by the users. We want this system to be able to improve our HVAC controls, to improve how much energy storage is stored in a battery on site, or to improve the mobility efficiency, and maybe if we're charging our electric vehicle at home, to really balance all of these systems together. So once again, I'd like to thank you all for listening, but also to thank my two PhD students that have been really working on this a lot, Kunid Sharma here and Chrissy Govertson, who are both working with this ecobee data set. So thank you, and I guess we can open the floor back to questions. So how does that sound?
Great. Thank you, Dr. Kane, very much. So if you have a question, please feel free to type it into the chat box. And it is possible that if you want to speak your question aloud, if you type it into the chat box, we can open up your line so that you can ask the question. Okay, Dr. Olu would like to speak, so let's see if we can open up your line, Dr. Olu.
Hi, Melissa. Can you hear me now?
Yes.
Yes, I can hear you.
Very well. Thanks a lot, Dr. Kane. I really enjoyed the presentation. I'm sure I'll probably try to see you when I'm on your campus on the 24th to 26th to visit with Dr. Brad Lehman. Yeah, we're doing some joint collaboration on NSF work, and I will be giving a lecture to his students. For the occupant load, I'm just wondering how the ecobee kind of take the data or the measurement. Is there anything attached to the occupant?
No, so this data comes directly from ecobee, this thermostat company, from people's homes. So these are thermostats that people bought from Best Buy or from Amazon or directly from ecobee, installed in their homes, or maybe they was sold to them by a HVAC professional. And when they set up the software, when you log into the mobile app, because all of these thermostats have mobile apps that go along with them, there's a checkbox that says, I want to donate my data to science. And if the person checks that box, then their data is anonymized and then aggregated into this database that is then released to the research community. So Northeastern had to sign a non-disclosure agreement to be able to use this data, but we can release these kind of broad scale.
More or less, some of the data is coming through convention, temperature type of, to be able to gauge the comfort level. Do you take into consideration the reflectant or the furniture that is in the space, or for judging the comfort level of individual, depending on which side of the house they are in? How accurate, or I know one cannot get an accurate data precisely, but are those factors in terms of what is in the space, also in the building envelope itself, taken into consideration for the
Yes, that's a
temperature?
great question, and really pointing out some complexities of this data and some challenges of working with it. So the nice thing about Ecobee thermostats is many of them come with remote temperature sensors. So a person can not only have the thermostat in their living room, but they can take another one of these battery-powered remote temperature sensors and put it in their bedroom or something like that. And it will try to kind of balance the temperature between both of those spaces and at least make the average of those two temperatures the temperature that the thermostat is trying to keep. And it'll do that based on the occupancy of those rooms. But yeah, there definitely is missing information in terms of some things that would cause people to decide whether they're comfortable or not comfortable. Radiant temperatures of like the sun through the windows, or certain characteristics of furniture, things like that that you mentioned are all things that aren't necessarily explicitly captured in this data. We can try to back some of that out kind of heuristically, but
Thank you
it's a
very
good one.
much. I
Yeah.
appreciate it. Thank you.
So Stevens brings up another good question of since the majority of people assume valve theory, would a good approach be to retrofit our current HVAC systems to mimic valve theory? And that's actually a very good question. I'm sorry, I may have misstated that it's about one third of people assume valve theory. So about a third of the population is mischaracterizing um, how our thermostats work. And that could be one option. And I think that really is going to be the future about when we design these automation systems, we need to adapt them to how people think they work. And so, when a person buys a thermostat, they're not going to say, "Oh, I am a valve theory mental model. I'm going to buy this thermostat." So, if we can make the thermostat not only learn about properties of the building, but also learn about properties of the occupants, I think that that's a great kind of vision for the future and future of occupant-centric controls for buildings. Um, Eric is asking another question. So, yeah, you're welcome, Stevens. I hope that answered your question. So, Eric is asking another question. So, what kind of things can we do now to help better control our HVAC systems while providing comfort to the occupants? So, it looks like Eric is asking me to give him the idea for the idea scale competition. So, I kind of gave you a bunch of overview of the area now, and I think that personally, the areas that I'm working in are being able to have these control systems better understand the occupants. And the trick there is deciding what are the important things to measure with the occupants. So maybe Dr. Olu had a really good point about that there's things that affect thermal comfort that aren't characterized by the data that we're currently collecting. So we wouldn't be able to personalize the systems if we're not collecting data that we need to personalize it over. And then there's other aspects as well that we can do to provide better occupant-centric controls, provide better comfort. I think there's really some interesting opportunities in how that interacts with the electric grid. And there's a bunch of opportunities there, and I think that was also kind of a bullet point of that idea scale competition. So I hope that did that answer your question, Eric, or feel free to follow up through chat, or we can open your line if you'd like. Great. Yeah, so we have a question here from Terrence, just kind of asking about how do I feel about the current state of mass-marketed smart control tools like the Ecobee thermostat or their competitors by Nest or Honeywell, um, or pretty much any of the other major thermostat manufacturers. They all also have some. Um, and I think that the bar for a smart thermostat right now, or by definition, is pretty low. Smart thermostat pretty much just means a thermostat that's connected to Wi-Fi. And I think that there's a whole lot more that can be done to make thermostats smarter. So what Ecobee does, that Nest is just now starting to do is have these remote temperature sensors. Ecobee acknowledges that the temperature throughout your home is not constant. It's not the same in your bedroom as your living room as your basement. And being able to control each of those in order to maximize comfort while minimizing energy use is a challenge. What Nest kind of their little niche or their specialty is, they try to learn a model of the building. And if you want it to be 65 when you get home, it will, or if you want it to be 70 when you get home and it's 65, it will know how long it takes to heat up that 5 degrees, depending on the outside temperature. So if it's really cold outside, it might take longer to heat up than if it was warmer out. So Nest tries to create smarts by modeling the building. Um, there's some smart thermostats out there that I think Nest might do this as well that try to kind of detect patterns of occupancy. And even if you say that you're not away, to actually try to reduce energy while you're away. But if it's wrong, that's pretty risky because that ends up with overrides then, people not trusting the thermostats, and ultimately defeating kind of the real benefits of controls. Trying to think of anything else really kind of key points of the thermostat market, but I think that there's a whole lot more opportunity, especially as these smart thermostats become smarter and start by kind of predicting both the building response and the occupant behavior, and on top of that, how it relates to the electric grid by trying to modulate load and shift load. You're welcome, Terrence. So Raj has a question of what happens when occupancy density changes at parties. So this is that classic case where you're inviting a bunch of friends over for your house for dinner or for a party, and it gets hot even in the middle of winter. Even in Michigan, you end up opening your windows because it's so hot inside. Just because, why is it? Because every person is a 100-watt light bulb. Essentially, they're generating 100 watts of power that's trying to heat up that room. So if you have 10 people in a room, that's a kilowatt heater in a room that you don't need to heat up with um, your control system. So then the question kind of follows of, can we employ predictive control coupled with electric utility smart meter as a demand response strategy? I think that's a separate question. I'm not quite sure how those two questions are related, because unless you're having parties at your house every day at 5 o'clock during peak electricity demand, I think that's a kind of a niche market. That's kind of a, if it works, will it matter? I'm not really sure it'll matter that much if you're trying to do demand response just for house parties. Um, but if those are separate questions, absolutely. So can we do predictive control coupled with electric utility smart metered for demand response? So that's both predicting the home response, predicting the occupant behavior, and predicting what grid prices might be in an hour, in 6 hours, something like that. So I think those are all important aspects that could help improve demand response through better controls. So if that answered your question there, Raj.
Great. Does anyone else have a question for Dr. Kane? Please feel free to type it into your chat box or let us know if you would like us to open up your line. While we're waiting here, I just want to remind everyone to go to jump.ideascale.com to find out more information. That jump.ideascale.com website is the website on which you would submit your ideas. And then there's a main website, and there's a link to that main website on jump.ideascale.com. And that main website is an Oak Ridge website, and it has a lot more information on how the process works, what the requirements are for participation. So please feel free to go to those websites to learn more about Jump into STEM. And now that a minute has passed, I think that we have wrapped up our Q&A session. I don't see any more questions. Apology if I missed anybody. And then Dr. Kane also wrote his email in the chat box, so if you're interested in emailing him directly, his email is right there. So with that, I want to thank everyone for joining today's Jump into STEM presentation. It certainly was very informative, and best of luck on your submissions.
Yeah, great. Have good luck everyone, and keep up the good work. So bye-bye.